Okay, hi everybody. So we have been discussing vector spaces, checking various examples, and a lot of these examples have involved sets where our objects are vectors, and we've seen that based on the way that we define addition among those vectors or multiplication by a scalar, that we may or may not have a vector space. So there's a relationship between the objects in our set and the operations that we define between them. We've seen that these objects don't have to be vectors in the strict sense of being in R2 or R3 or R4. We've worked with an example where our vectors were actually polynomials. So a very common types of vector spaces are where our objects are actually matrices. So let's consider a set V where we're going to consider our objects as all 3x3 matrices. And we're going to define the usual matrix operations in the sense that we're going to define the usual addition of two matrices. We're not dealing with multiplication here. We're adding vectors in our space. So we're going to add two 3x3 matrices, and we can add matrices as long as they're the same size. And we have our usual scalar multiplication by a matrix, which tells us we just multiply every entry in the matrix by that scalar. So let's check to see whether this set of objects with these operations satisfy all 10 of the axioms that we need to check for a vector space. So let's let A, B, and C denote 3x3 matrices in our space, and C and D, lowercase c and d, are going to be scalars. So we can check these pretty quickly. If I take a sum of two matrices A plus B, they're 3x3. The resulting matrix is going to have the same size. It will be 3x3, and therefore this set is closed under matrix addition. Is it addition commutative? Yes, it is, because addition of numbers is commutative. So we've discussed this property of matrix addition before. Matrix addition also satisfies the associative property, so that is great. We have a zero vector, namely if I add a 3x3 matrix of all zeros, we add that to any other 3x3 matrix, we'll get that same matrix back. So we have a zero vector in this case is a zero matrix. We want to make sure that for each matrix, we have an additive inverse, which here we would get by just multiplying every component of the matrix A by -1. So if I add this to the matrix A, right, each term cancels out, and we'd wind up with the zero matrix back. So we've got a unique additive inverse for each matrix A. Multiplying the 3x3 matrix by a scalar will result in a 3x3 matrix. So we're closed under scalar multiplication. Distributive properties, both of these hold. We have this associative property for multiplication. And we also have that when I multiply a matrix by the scalar 1, we get that original matrix back. So our multiplicative identity is the number 1 in this case. So here we can see that we can have more abstract looking objects that can construct our vector space. Namely, we can have objects be matrices, and we define some operations on those matrices. And the way that we've defined matrix addition and scalar multiplication by a matrix earlier satisfy all 10 of these axioms. So this would give us a vector space. Okay, so let's consider another vector space of matrices potentially. So now let's consider V, which is our set of objects are going to be all 2x2 triangular matrices using our usual operation. So we're not going to change the way that we add two matrices. We're going to use the typical matrix addition and the typical scalar multiplication by a scalar as well. So let's take two matrices that could be in this space. So over here, this matrix A, this is triangular. So by triangular, that means all of the entries either below the diagonal or above the diagonal are zeros. So this first matrix A is an upper triangular matrix. This second matrix B over here is a lower triangular matrix. All of the entries above the diagonal in this matrix are 0. And so when I add an upper triangular matrix with a lower triangular matrix, the resulting matrix may not be triangular, right? We could have non-zero entries everywhere. So this addition is not closed under this set. So I could take the sum of two triangular matrices and get something which is not triangular back. So this is not a vector space. However, if we just tweak this ever so slightly, and instead of saying triangular, I say upper triangular 2x2 matrices, then you can verify not just that it's going to be closed under matrix addition, but all of the other axioms would hold as well. So if we take the set of all upper triangular 2x2 matrices with the usual operations, that would be a vector space. If I took the set of all lower triangular matrices, that also would be a vector space. But if I'm considering the set of all triangular matrices, both upper and lower, this is not a vector space because we are not going to be closed under addition.